In this section, we're going to be applying what we learned about scatter plots and correlation into looking at a regression line that best fits some of those scatter plots. For instance, if we had a scatter plot that looks something like this, it seems like there's a lot of different lines that could fit through here. For instance, we could have a line that looks like it's a pretty good fit, but this line looks like a pretty good fit as well. So again, there's a lot of different lines that we could run through here. So the regression equation that we want to use is the mathematically best fit line. So the regression equation is the mathematical line of best fit. Now, there's a lot of information that goes into calculating this, but we're going to rely on our calculators to help us through some of those. So again, regression is the mathematical line of best fit. So the regression equation is basically the line that minimizes the distance from each point to the line. So each point to the line is an error, and so it tries to minimize those distances, and it finds the line that minimizes all those distances, and that's our line of best fit. So the line of best fit is going to look like y hat equals, and I'll show you where you can find this on your calculator too. So in our calculators, we would go under Stat, Calc, and then we see all these different options. We're used to using like one variable statistics, but we're going to be using linear regression AX plus B. And so that's our line of best fit that we'll be looking at, is AX plus B. Now, if we were to graph this, this is a line. So that's why we're talking about linear regression. We're not talking about quadratic or curves or cubic. We're just talking about linear regression. Now, if you remember your rules from algebra, in this particular case, A would equal the slope of the line, and our value of B here would be the y-intercept, where it crosses the y-axis. Now, y hat is my predicted value, and it's an estimate based on a sample. And what we can do with our line of best fit then is, if we're given a value of x, then we can predict our value of y based on this line. Now we have to be careful. If, let's say, these values on our x-axis run from 1 to 10, we don't want to do prediction clear out here at 20. We want to do our prediction within the data set or very near the data set. So you have to be very careful about interpolating or trying to speculate what's going on beyond the data that we've collected. Now these are pretty easy to work with. Our calculator again is going to do a lot of the work for us and leave us just to look at the interpretation, which is the important part. As we're working and looking at our steps, and again we're looking at linear regression, the first thing we need to do is to determine whether it's reasonable to even use linear regression. So step one, we need to go ahead and look at our correlation coefficient, and we need to test HO versus HA for that correlation coefficient. Remember, that was rho equals 0 or rho not equals 0. And again, rho equals 0 is there's no linear correlation. And rho not equals 0 means there's some sort of linear correlation. Now, if we can establish that there is some linear correlation, then from here, this is when it's appropriate to find the line of best fit. And again, that was from up here, our line of best fit was AX plus B. If we find there is no linear correlation, a line of best fit doesn't really seem to make sense so much. Okay, so that's our first thing, is to test HO versus HA to see if there is a linear correlation between the two random variables. And then if there is a linear correlation, go ahead and find this regression line. Second step we would look at is simply just to enter the data. And usually we have L1 and L2 that we're looking at. Third step is to calculate our regression line, and I'll show you the calculator steps real quick. And again, that was under Stat, Calc, Linear Regression, AX plus B. So calculate the line of best fit. And again, that line of best fit is the y hat equals ax plus b. And we find that by going to stat, calc. So again, we go to stat, calc, and then we choose our fourth option on my calculator. It might be different on yours. Linear regression ax plus b. Okay. Now once we find that linear regression, we can do a scatter plot, and we can do quite a few other things, but I kind of think the scatter plot is better up here in this step. And then if we want to, we can do prediction. And again, we can only do prediction when we're within the range of the data that's been collected. So we can only do prediction if that's appropriate here. We only want to look at values that are close to our original data being collected, because we can't predict what's going to happen, let's say 1,000 years from now. We can look at trends and we can assume some things and take some guesses, but we really only are very good at predicting close to where we're at right now. So let's go ahead and look at a data set. Now a lot of times you're going to be given more information than you need to run through the hand calculations, but basically for what we're looking at, we're going to let the calculator do the handwork for us. Okay, so for our first example, we're going to be given some information about IQ scores. And so we have two random variables. We have IQ scores for husbands and IQ scores for wives, and they're related. And so we have n equal 20 pairs. So we have 20 pairs of data that relate a husband's IQ score and a woman's IQ score, a husband and a wife IQ score. And what they tell us is that after crunching the data, we are given the prediction line of y hat equals negative 6.35 plus 1.08x. Now what I don't know here about is x and y, and we always need to be careful that we define these. I don't know which one is husband and which one is wife in this particular case, so we need to clarify that. So to get started, let's go ahead and look at x equal husband's IQ score. And of course that leaves y to be wife's IQ scores. So what we can do is if we have a husband's score, we can use that to predict the wife's IQ score. So y hat would be the predicted wife's IQ score based on the husband's. Now some other information that they're providing to us, they're also letting us know that we have a correlation between these two random variables, and they tell us that R is equal to 0.841. Now remember, this is the sample correlation coefficient from our last section. And then we're given this information, if appropriate, let's go ahead and look at the predicted IQ of the wife. So that's y hat. Given, we know the husband has an IQ of 94. So what we're looking at here then is our full steps. They've already given us all of our summary information. We don't even have to calculate y hat here. But we need to start with our first step. So our first step is going to be to test HO versus HA. We need to know whether it's even appropriate to think that this is linear. So we're checking to see if R equal 0.841 is basically a correlation coefficient that's different enough from 0. And I think that it is, but let's go ahead and run through the steps. So it's rho equals 0 versus rho not equal to 0. And so this is no linear correlation, if you'll remember. And this is some linear correlation. It doesn't say how much or which direction, it just says there is a linear correlation. Second step, let's go ahead and test this at the 5% level of significance. Because we don't have raw data, let's go ahead and look at critical values. Now remember, for our critical values, I need two pieces of information. I need to know my sample size, which was 20 pairs, and my level of significance, which is 0.05. Now this sheet for these correlation coefficients can be found in my math lab, and I'm also have given you one in class by now probably. So we'd go to my courses, if you're not already in my math lab, and get into my math lab. And then here under tables, you would choose critical values of the linear correlation coefficient R. Now we are at sample size 20 here. So here we are at 20 and we're at 0.05, so our value here is 0.444 is our critical value. So let's go ahead and snap that in. And so again, we are looking basically at the cross section of 20 and then 0.05. So we can see that our critical value is this 0.444. Now remember, our R value was 0.841, I believe. Yep, 0.841 from up here. So the next step we're going to do is to go ahead and look at our test statistic. And that's given to us in this case, is just our R value. Now if we were using the p-value approach, we'd want a t-score, but we don't have raw data, so we can't do that in this case. So R equals 0.841. We're going to want to go ahead and make some sort of a decision. So in this particular case, the absolute value of 0.841 is greater than our critical value of 0.444. So therefore, the triangle with 3 dots means therefore we would reject HO. And if we reject HO, what we're saying is the correlation coefficient doesn't equal 0. So when we summarize this, we can basically look at this and say, you know what, it looks like the data supports the conclusion that there is some linear correlation between the two variables. So there is a linear correlation between the two variables. And the two variables are husband IQ and wife IQ. And the whole idea of this is we want to know if it's appropriate to use this linear regression. So there is a linear correlation between husband IQ and wife IQ, so it is appropriate to use linear regression now, because we've established that there is a linear relationship or a linear correlation, so linear regression makes sense. Okay, so that's kind of the end of that first step. We have to establish that that's true. Second, and again I'm going back up to these steps up here. Second, enter the data. Well, we've already done that in this case, and they've already given us our line of best fit. And then we need to use a prediction if appropriate. So step 2 is done. Step 3 they gave us. So step 2 is given. Step 3, they gave us that y hat is equal to negative 6.35 plus 1.08x. And then our next step 4 would be using prediction. So basically we want to predict the wife's IQ when husband's IQ is, I think we said 94. So basically we take y hat equals negative 6.35 plus 1.08x. Now one thing you have to be careful about here is they don't always list these in the direction that's given. So for instance up here, we have ax plus b. A is the slope, b is the y-intercept. And then down here, when we're given that regression equation, the first value doesn't have the x with it. So my first value is the y-intercept, and the second value is my slope. So we have to be careful how we plug these in, and they're used interchangeably. So you need to be aware that the coefficient that's in front of the variable x will always be your slope. The constant that's by itself without the variable is always the y-intercept. So let's go ahead and plug that in. So this is my prediction of the wife's IQ, negative 6.35 plus 1.08 times 94. Okay, so let's go ahead and plug this into our calculators and see what we can come up with. So negative 6.35 plus 1.08 times 94. So we have our prediction here of 95.17. So let's snip that in. So for a husband's IQ of 94, the equation predicts a wife's IQ a little bit higher here of 95.17. Okay, so that's what's going on here. And of course there's going to be exceptions to this rule. This means the overall trend or the overall average of what's occurring. So before we can use linear regression, we need to establish that there is a linear correlation first, and then after I find the values for my linear regression, then I can actually go through and do some prediction. Now another interesting thing that we can do is we can graph these. Now I already have my y equal here that I'm used to graphing with. Let's go ahead and just put in negative 6.35 plus 1.08x. Now we might have to adjust our viewing window here. But basically, my x's are my husband's IQs, my y's are my wife's IQ. This is a positive sloping line. So what this is saying is as the husband IQ goes up, so does the wife's. So they're positively correlated. And that value of 0.841 for R tells us that. Okay, let's go ahead and look at an example where we're given raw data, and then based on the raw data, we're asked to find some values. So for this example, we're going to look at two data sets. They're correlated, so we need to make sure we enter them carefully to make sure the X is always associated with Y. And we're looking at a population of bears. And out of this population of bears, we took a simple random sample of 6 bears. So we have 6 bears that we sampled. And based on these 6 bears, we took 2 measurements. We took their chest size, their chest circumference in inches, and then we also looked at their weight in pounds. And we're trying to see if we could correlate these things to maybe, if it's a high enough relationship, maybe I could predict their weight based on their chest size, and that would make it easier to do some measurements in the field. So for a bear who has a 41-inch chest, his weight was 328 pounds. And the second bear who had a 54-inch chest, his weight was 528 pounds. And of course we had 4 other bears that we checked on. So let's go ahead and write out the rest of this data. And then we're trying to check to see whether there's a relationship, a linear correlation between chest size and weight. Something like as chest size increases, so does weight. And we have to be careful about how we do this because we have to run through the actual test to see if they are correlated. So I think the first thing that we'll want to do is we'll want to check to see if there is a linear correlation, and let's go ahead and use the 5% level of significance. So let's do a scatter plot first, because that always gives us a good idea of whether a linear relationship exists. So we go to second, stat plot. We go ahead and turn our plots on. Whoops, I better enter my data first. Let's go back out. Stat, edit, clear out my data, and then let's enter the bare data. Okay, so we want to be careful that 41 is associated with 328, 54 with 528, so we have to be careful how we enter the data. So let's go ahead and enter my X values first. Because I'm trying to predict weight. I'm not trying to predict chest size. So those are my X values, and we'll annotate this on our notes as well. And these are my Y values that I'm trying to predict. It's 580, 296, and 503. 296 and 503. Now if you notice in your data up here, each one has a corresponding X and a Y value. So let's make these notes. Chest size is my X value. Weight is my Y value. This is what I'm trying to predict. Now in my calculator, this was L1, this was L2. And it's important to write those down and keep track of them, because otherwise it gets kind of complicated. It's hard to remember which is which. So let's go back into second stat plot now. Go into that first one, make sure it's turned on. This first option is our scatter plot. My X values are L1, my Y values are L2. And we have to sometimes change our viewing window after we hit graph. This is that old linear regression line. I need to go get rid of that. So let's go ahead and Y equal and clear that one out. Let's graph again. Now if you notice, nothing is showing up here. So we want to go to zoom, and we want to look for zoom stat. So zoom stat, and this is what it's giving me for a scatter plot. And basically what the zoom stat does is it goes and finds the data for you on the screen. This does look very linear. So to get started, it seems like looking for a linear relationship or a linear correlation between these two random variables is appropriate. Okay, the next thing we want to know, let's go ahead and calculate our correlation coefficient. So we can do our correlation coefficient under stat, tests, and we want to look under our linear regression t-test right here. So for our linear regression t-test, again, X-list is L1, L2, frequency is 1. What I'm checking for is to see whether they're related or not. And this regression equation we'll talk about later. And I'll show you how to calculate that. For now, we're just looking for our value of R. Now the value of R, we have all this stuff going on here, but R is right down here if I scroll down. And we can see that that value of R is really big. It's very, very close to 1.985878. So this is important. This is our correlation coefficient. This is the strength of the linear relationship, and it looks like it's a strong, positive linear relationship. So this is the information I need to go ahead and get started to check to see if there is a positive correlation or a negative correlation or no correlation at all. And because this is really close to 1, I'm very confident that we're going to end up rejecting HO. So we're going to check to see if there is a linear correlation between, in this particular case, chest size and weight. Okay, so this is an actual hypothesis test. So my first step is to do HO versus HA. We're checking to see if the linear correlation coefficient rho is equal to 0 versus not equal to 0. So this is no correlation, no linear correlation. And this is some sort of linear correlation. It doesn't tell me if it's positive or negative, strong or weak. They're just saying there's some linear correlation. In this particular case, let's use alpha equal 0.05. Next step, we're going to find our critical values, I should say. Remember, the critical values come from that table. So we had 6 bears that we measured. So we'd be under 6 right here. 5% level of significance, 0.811. So let's go ahead and snap that in so we can see where that's at. And those are going to be my critical values. Now I'm looking for anything that's more extreme than these critical values. So if I end up with anything more extreme than 0.811, then I'm going to feel pretty confident about rejecting HO. So again, that comes from here because I have a sample of size 6. And I have alpha is 0.05 and these intersect right here. So my critical values are plus or minus 0.811. Now here my test statistic we already have is just our R value. And remember that R value is very, very high. It was 0.9859, we'll say. We'll round it to 4 places. Then we're going to go ahead and make some sort of a decision. And we make a decision here by looking at the absolute value of R. And we want to see if it's greater than our critical value or less than our critical value. Well, we can see pretty clearly here that it's going to be greater than our critical value. So we have the absolute value of R, which is 0.9859. And it is greater than our critical value of 0.811. And I could have done the negative here, but it doesn't really make sense because I'm looking at our absolute value, so I just always look at the positive. Therefore, we would reject HO. That would be our decision. And because we reject HO, when I talk about my summary, it's appropriate to use linear regression. So the data supports a linear correlation between the 2 random variables. And the 2 random variables were chest size and weight. So, linear regression is appropriate. Okay, so now we know linear regression is appropriate. So this was my first step in linear regression, checking to see if there's a linear correlation. Step 2 is to go ahead and enter the data, which we did. And after we get done with step 2, let's go ahead and scroll up to the top again and check out our steps. So enter the data, we have that. Calculate the line of best fit, and then do any prediction that's being asked. So enter L1 and L2, which we did. And we already entered this because we had to use these values to find our correlation coefficient for my hypothesis test. So enter L1 and L2. Find the line of best fit. And this is our regression equation. Now, we actually did this, but we just didn't pull this information out. So let's go ahead and look at this calculator output one more time. So we would go to Stat, Calc, and we'd come down here to Linear Regression, which on my calculator is option 4. Let's see if I can find my mouse here. Here it is. Okay, and so then we would go down to linear regression ax plus b. And so this looks pretty familiar. This is my x list, this is my y list. My frequency list is just going to be blank because I don't have a frequency like these are occurring 10 times or something. But this is interesting, store regression equation. So I don't have to type it in again later. What I can do is I can have this store it in y1, and then I can plot this. So in order to do this, we go to variables, y variables, function, and then I can store it in any of these y equals that I want. And I'm just going to go ahead and store it in the first one. And let's go ahead and hit calculate. We'll do a screenshot of this first in case we need to look back for instructions. And then let's hit calculate. And here's our regression equation. Now also, not only is this my regression equation, but it has been entered automatically for me in my y equal. So this is my ax, this is my slope, this is my y-intercept. I should be able to come over here to y equal and see that 16.32 and the negative 330, and it carries it out much further, of course, for my line plot here. Now if I want to see what this regression line looks like on my scatter plot, I would just hit graph, and here is that regression equation right here. So this is what it looks like visually. So the calculators are very helpful here. They give us a lot of really good information, and they give us a nice visual of the relationship between x and y here. So my line of best fit, I can go ahead and pull off of here. Because a is in front of the x, this is my slope. And because this stands alone as b, this is my y-intercept. So my regression equation is y hat equals 16.3216 x plus b. B happens to be negative, so I'm going to have negative 330.390. So this is my regression equation, and if I were to graph the regression equation, it would be this blue line right through here. So that's my line of best fit. Now we have to be careful about how you enter this. A lot of times in my math lab, it's not going to look for y hat equals ax plus b. It's going to look for b plus ax, or vice versa. So remember, the slope is always in front of the x, no matter which order these come in. Now let's go ahead and look at a predicted value, because that seems appropriate to look at a predicted value here. That's our fourth step if prediction is appropriate. So find the best predicted weight. Of a bear with a chest size of 40 inches. Now 40 is somewhere down here on our x-axis, and what I'm trying to do is to find that and then see where I am at on my regression line. So there's a couple different ways that we can do this, and I think it's best to use both ways actually. Remember, y is my weight of the bear, and x is my chest size. So 16.3216x, in this case is 40 because I'm trying to predict, minus 330.390. Now remember, x is my chest size. So let's go ahead and plug this into the calculator and see what we get back out. So I'm going to do second quit. We'll go back to that graph. And then this is not going to be exact because I'm rounding this, but it should be pretty close. So 16.3216 times 40 minus 330.390. And so here we can see 322. Now this is weight, so this is pounds. So 322.474 pounds. So 322.474 pounds. Now be careful, make sure you round as my math lab is asking you to. Now one other thing I want to look at here is back to my graph. Once I see my graph, I can go to second calc, and I can go to value here, and I can plug in any value I want. Now for my prediction, let's go ahead and plug in 40 to see what we get back out. And here's 40. They're showing me right on here. This is where 40 is on my X, and that's equal to 322.47472. So they're showing me that this is the predicted value that I'm looking at. So you can do this graphically as well. And if you notice at the top of this, it also gives me my line of best fit. It shows me that predicted value. So I really like this scatter plot with the line drawn on it, because it really gives me a good idea of where that value is. So this is that point when X is 40, and that's telling me the same thing right here, and my Y value is 322.475, we'll say. Now you might say, well, wait a minute, they're a little bit different. This is 474, this is 475, but look, I rounded here. They carried it out the full distance, so I probably think this one is a little bit more accurate. The more you round, the more you're going to be off. So if you've done a problem in my math lab for your homework and it says it's incorrect, maybe you over-rounded. Maybe you should go back to the original here. So again, I really like this graph. It gives me my regression equation, and it gives me my line of best fit, and it also shows a predicted value. Now most of the problems you're going to be looking at are very similar to this. You'll be entering data, so make sure you enter your data correctly, because that can be one of the big problems. Even just a single value off could really throw things off quite a bit. Good luck on this homework assignment. If you have questions, please bring them to class, stop by my office, or you're welcome to use the Math Center as well. Good luck.